Hello and welcome to this next lecture in pattern recognition. With the last lecture we have discussed, we completed our discussion on kernel based methods. So, with that we kind of completed the part of the course which discusses about learning classifiers. Okay. So, we can take a global look now and ask what all have we done so far, right. So, in this course so far we discussed various strategies for learning classifiers, right. We started with pattern classification, said the classifier design is what admits lot of mathematical structures, and we discussed different strategies for learning classifiers. So, specifically we considered the base classifier, the optimal base classifier, different methods for implementing it by learning class conditional densities. Then we looked at various linear classification regression techniques, perceptron, least squares, LMS, special linear discriminant. So many of these techniques we looked at. We looked at various pros and cons of them. Then we went into statistical learning theory to show what kind of bounds we can put on them. And then we looked at strategies for learning nonlinear classifiers. So, we just concentrated so far on some general techniques for learning classifiers given data, both linear and nonlinear classifiers, and some theory of statistical learning which also deals with this. So, one question that we never address really is what features does one use, right. In all our discussions so far, patterns are represented as feature vectors, right. Patterns are abstract for us and patterns are always some d-dimensional feature vectors. And we have never in this course said anything about what kind of features does one use. Very beginning of the course we have seen many examples of specific pattern recognition tasks, and there we discussed the kind of features people use in those examples, and the overall import is that features are very much problem dependent, which is still true. So, what features to use very much depends on the problem and the kind of pattern. As I said, if I am doing a speech recognition task, I would have a one dimensional signal and I may do some frequency content out of it as my features. If I am doing a face recognition task, so it's image as the feature, and the kind image as the pattern, and the kind of features I measure would be totally different. So, in general features are very much problem dependent. Okay. Essentially, one heuristically decides on what kind of quantities are relevant for the classification decision, and also what kind of quantities are easy to measure, easy to calculate, and that is how one comes up with a decision on what features to use. Okay. Of course, in practice the final classifier would very much be dependent on the features used. So, even the so called base optimal classifier is optimal in the sense given that particular feature vector and the corresponding underlying class conditional densities, no other classification rule can do better. That is all it means. It does not mean that you cannot, on that problem we can't do better. Obviously, if I change the features, I may be able to do better. So, while we cannot give any general theory of what features to measure, it is still possible to talk about, if I can measure so many features, out of that can I develop features which are useful. So, one strategy, what is called feature selection, is that we start with many different measurements. We measure whatever we think are possibly relevant, and then out of that, given our training samples, try and unearth a good subset of features. Right. This is known as the feature selection problem, and the problem we want to address here is essentially which subset of features have the best correlation with the class label. So, we are asking, given my training data, what is the best subset of features can I use? So, looking at the training data, I am asking which features have better correlation with the class label, which features have less correlation with the class label, which features seem to give me the best discriminative information. So, there are some information theoretic ways of formulating this question, saying which subset of features gives me the best information regarding the class label, and we can use such notions to decide which subset of features to select. Okay. So, there are some general techniques which say, okay, if you can measure these 500 different features, I might be able to provide you with some 50 good subset of features, right. These are computationally expensive, but they are often useful. But in this course, we will not be considering feature selection. Okay. These techniques are computationally rather expensive, and it's difficult to implement a completely theoretically justified method. So, very often they turn out to be heuristic. With that, and also because it takes us a little outside the purview of what we want to discuss here, we will not be considering this. However, I would like all of you to know that there is a lot of work on how one can select a subset of features. As I said, there is also another way of looking at getting better features. Given that I have measured these features, can I manufacture new features out of these features? For example, maybe certain linear combinations of these features may give me better features for discrimination. Okay. So, there are also techniques to transform the original features vector into a new feature vector. We want to do it for many, we want to do the features. For example, we may want to make them uncorrelated, or we may want to make them better at classification, or we may want to do dimensionality reduction. I may ask, can I, instead of having this 100 dimensional feature vector, can I have some 50 dimensional feature vector? Of course, just dropping a 50 of them may not be the best solution, but if I transform them first and then drop a 50, it might be better, right. So, I may want to transform them to get a better dimensionality reduction. Okay. One such very popular technique is called principal component analysis, or PCA for short, and this is a very, very important technique in many different problems of data analysis and machine learning, apart from pattern recognition. So, whenever you have training data and you want to understand the geometry of the training data, to ask how many dimensions in the vector are needed to capture most of the training data. So, principal component analysis is a good technique. It is in general used as a very general purpose dimensionality reduction technique given some data. So, we will consider that in detail in this class. So, we can think of PCA as a useful linear transformation of the feature vector. So, given the feature vector, you want to find a linear transform to transform the feature vector into some other space, or linearly transform into some other space, and that is useful for classification. Okay. In the dimensional reduction sense, we essentially want to project the data onto some lower dimensional subspace, right. The linear transform would be projection actually. So, if I may have a d-dimensional feature vector, I may want to project it onto an m-dimensional subspace of the d-dimensional space. Okay. So, we can in general define PCA in two different ways. A PCA is a projection of data onto a subspace such that, one, variance of the projected data is maximized. That is, even though I am projecting onto an m-dimensional subspace, most of the variance of the data is captured by the projection onto the m-dimensional subspace. So, given a fixed m, which particular m-dimensional subspace will capture as much of the variance of the original data as possible. 2 is, if I want to approximate the original feature vector with its projection, I want to minimize the mean square error. So, I want to find that m-dimensional subspace such that approximating a feature vector with this projection in the sense of mean square error is best. As it turns out, the solution for both is same, right. So, that is the PCA. We will see how to derive what this particular transform would be, but whether I want to think of it as best approximation in the low dimensional subspace, or for a fixed m, both are for a fixed m, for a fixed m capture most of the variation in the original data, the final solution turns out to be the same transform. Okay. So, that is what PCA is, that is what we are going to consider now, and I just want to want you to understand that here we are not considering the class label information at all. We are just looking at data, all the data, and asking if I want to project it to a smaller dimensional subspace, which subspace will give me the best approximation, right. We are not bothered about based on the class level information, which is the best approximation. So, here this is nothing to do with the class label, we are just given large set of data vectors, what is a best low dimensional representation of the data vectors. Okay. So, let us start to define the problem. Let us say we first want to look at it from the point of view of dimensionality reduction. Let x1 to xn be the given data. As I said, now class labels are not important. So, we will only look at x1 to xn. Let us say all of them are d dimensional. We want to project it into m dimensional subspace. Right. So, let us say u1 to um denotes the orthonormal basis for the m dimensional subspace. So, ultimately you want to determine the vectors u1 to um because they determine the subspace. So, the subspace of course is given by its basis and we will choose a orthonormal basis. So, let us say u1 to um is an orthonormal basis for the m dimensional subspace. And let us say because that will be a subspace of Rd, if I add um plus 1 ud, it should become an orthonormal basis for Rd. So, um plus 1 to ud define them to be those orthogonal vectors, which when added to u1 to um become a orthonormal basis for Rd. So, u1 to um is the orthonormal basis for the m dimensional subspace I am looking for, u1 to um plus 1 all the way up to ud is the extension of this basis to the whole of Rd. So, because this is an orthonormal basis, any xi can of course be represented as a linear combination of the vectors u1 to ud, and the coefficient of the linear combination will be simply xi transpose uj because it is an orthonormal basis, right. So, xi can be written as sum over j is equal to 1 to d xi transpose uj uj. Okay. So, it is written as a linear combination of these basis vectors uj and the coefficient of the linear combination is xi transpose uj. These are the standard representation in any orthonormal basis. Now, let us say xi tilde is the approximation of xi in the m dimensional subspace. Okay. Because in the m dimensional subspace which is spanned by u1 to um, xi tilde can be written as zij uj, j is equal to 1 to m. So, zij are the coefficients in the uj coordinate system for representing xi tilde. In addition, we will have a constant, right. We will put a second term which is a constant, so that if there is any mean to be taken care of, right, there is always better to take care of it with an extra constant to get a low mean square approximation, an extra. So, because this is a constant and whatever is in the m dimensional subspace can easily be accounted for by jij, the part of the constant which is not in the m dimensional subspace is what we have to worry about. So, that we will write it as j is equal to m plus 1 to d beta j uj. Right. Now, you can see that this expression is independent of I, right. This term does not depend on the index I. So, this is a constant for all xi. It is simply some constant vector which is in the orthogonal complement of this m dimensional subspace. The only reason for putting it like this is that essentially instead of just representing it in terms of these uj's, there might be a constant which when added might lower my mean square error. Of course, if I do not need the constant will turn out to be 0, that is when I optimize, but having a constant will help me to find a better approximation. Okay. So, what is the task now? We have to find zij bj to get the approximation with the least mean square. Of course, we have to also get uj. So, we will solve the problem in 2 steps. Given any particular uj, that means given any subspace, what are the best zij and bj's in terms of uj's? Then I will write the mean square error and find the best zij's and bj's. So, ultimately my mean square error now only depends on uj. Now, I can minimize the mean square error by choosing the right uj. So, we will first want to find the best zij's and beta j's to get a good approximation. Okay. What is my approximation error? I want xi to be close to xi tilde. Xi tilde is my low dimensional approximation. So, my error is xi minus xi tilde norm square summed over is equal to 1 to n divided by 1 by n. This is the mean square error. This is the error, this is the square of the error I add and divide by 1 by n to get the mean. So, mean square error is what I want to subtract. Now, we know that xi till xi is given by this xi transpose uj, whereas xi tilde is given by up to it is some zij uj, and from plus 1 it is beta j. So, if I want xi minus xi tilde up to xi as xi transpose uj as the coefficient and xi tilde as zij as the coefficient. So, this is xi transpose uj minus zij into uj, j is equal to 1 to m. From m plus 1 to d, xi still has xi transpose uj, but xi tilde has beta j. Okay. So, I left everything is still the norm square. Xi minus xi tilde vector is represented in terms of uj's like this. Now, because u's are an orthonormal basis, if I have a linear combination of u's and I want the norm, norm square is simply equal to the square of the individual coefficients. So, this is 1 by n summation is equal to 1 to n, that comes from this j's thing, and here I have to square all the coefficients. So, j is equal to 1 to m xi transpose uj minus zij whole square plus j is equal to m plus 1 to d xi transpose uj minus beta j whole square. So, this is the mean square error. Right. So, I want to minimize this to find zij and beta j for given u's. Okay. So, how do I find them? We first have to take partial derivatives of j with and equate it to 0. So, I have essentially find zij and beta j. So, first let us look at derivative with respect to zij. So, if I take any indices s and t and I want derivative with respect to delta z s t, with respect to z s t, if I want partial derivative, there is only one term in this entire expression that contains z s t, that happens when I takes the value s and j takes the value t, and that term is nothing but xi transpose uj minus zi, that is xs transpose ut minus zst whole square. So, if I differentiate that, I will get this 2 into xs transpose ut minus zst equated to 0. So, what does that give me? That gives me zst is xs transpose ut. So, zij is xi transpose uj. So, essentially to find the coefficients of representation of x tilde with respect to the first u1 to you might as well use it as the same thing as the original x's, that is xi transpose uj. Okay. What about beta? If I want to differentiate with respect to particular beta t, that happens when the j takes value t. So, I fully remains. So, the derivative with respect to a beta t will be 1 by n summation is equal to 1 to n, derivative of this with respect to beta t, that happens only when j is equal to t, and this term does not have any betas. So, only this will come, that will be 2 xi transpose uj minus xi transpose ut minus beta t. Okay. So, for any t greater than m plus 1, only for t greater than m plus 1 we have beta t's. So, del j by del beta t equal to 0 implies 1 by n I is equal to 1 to n 2 times xi transpose ut minus beta t is equal to 0. If I expand this, I get 1 by n, 2 will anyway go. So, I will get 1 by n summation beta t, that will be n beta t by n will be beta t. The second that will come on the one side of the equality, that will be equal to what? 1 by n summation is equal to 1 to n xi whole transpose ut. Right? So, this gives me beta t equal to 1 by n summation is equal to 1 to n xi transpose ut. This is nothing but mean of xi. So, let us represent it by x bar. So, beta t is x bar t ut. So, my best approximation in the m dimensional subspace, given an m dimensional subspace, that is u1 to um and um plus 1 to ud, is for the first m components I use xi transpose uj as my coefficients, and for all the remaining one the constant I have to put is x bar transpose uj. Essentially, if x bar is equal to 0, I do not need it. If x bar is not 0, I need this constant. So, this is my best m dimensional approximation. Okay. by m-dimensional approximation, we mean the xi tilde vectors live in an m-dimensional subspace of d-dimensional space. Of course, this is a linear combination of the vectors u1 to ud. Each of the vectors u1 to ud are vectors in Rd. So, the right hand side of this is a d-dimensional vector. Okay. There is no question about that. So, this expression does not show that xi tilde is an m-dimensional vector, but the expression is such, we will see shortly how it happens, that essentially xi tilde lives in an m-dimensional subspace plus a constant, right. This constant is independent of I, right. So, except for a constant, xi lives in an m-dimensional subspace. So, if I know this constant separately, or let us say if x bar is equal to 0, which I can always take, then these m numbers xi transpose uj will completely specify xi tilde. That is what is meant by it's in a m-dimensional subspace. Okay. So, this is xi tilde. This is the best representation we get for a given juice, and we know that xi is this. So, if you want xi minus xi tilde, the first m components, the first m uj's, it is same. Xi tilde here is j is equal to 1 to m, xi transpose uj, and here also is the same thing. So, for j is equal to 1 to m, the uj's coefficient, if I take xi minus xi tilde will be 0, only this will survive, right. So, I can now write xi minus xi tilde as j is equal to m plus 1 to d, xi's coefficient for uj now is xi transpose uj, whereas xi tilde's coefficient is x bar transpose uj, only from j is equal to m plus 1 to d. So, this is my error. So, the norm square of the error will be what? Because once again, because uj's are an orthogonal basis, uj's are orthogonal vectors. If I take norm of this, that will be simply equal to squares of this, because uj's are orthonormal vectors. So, that will be xi transpose uj minus x bar transpose uj whole square, which I can always write as xi minus x bar whole transpose uj whole square. So, for a given I, my square of the error xi minus xi tilde norm square is sum j is equal to m plus 1 to d xi minus x bar whole transpose uj whole square. Okay. So, my actual j, my actual mean square error is sum of this over I is equal to 1 to n divided by 1 by n, right. So, my j is 1 by n, summation I is equal to 1 to n, xi minus x tilde whole square, which is this. So, I can write that as j is equal to m plus 1 to d xi minus x tilde transpose uj whole square. Now, xi minus x bar transpose uj is a scalar, right. So, I can write it as xi minus x bar transpose uj or uj transpose xi minus x bar. So, I can write the square as I first interchange the two summations, both are finite summations, j is equal to m plus 1 to d 1 by n, I is equal to 1 to n. I write this square as 2 times uj transpose xi minus x bar into xi minus x bar transpose uj. Okay. By writing like that, now I have a very interesting structure here. Right? Now, I can work it out that this, because these uj's do not depend on I, the uj transpose can come out of the I summation, and this uj can also be outside the I summation. So, I can write that as summation j is equal to m plus 1 to d uj transpose 1 by n summation I is equal to 1 to n xi minus x bar transpose uj. So, what I have here is a quadratic form, right, uj transpose something uj, and this something is a matrix, right. This xi minus x bar is a d by 1 vector and xi minus x bar transpose is a 1 by d vector. This is a d by d matrix, is known as an outer product. I hope many of you have come across this earlier. This is called an outer product of two vectors. So, I am summing over I is equal to 1 to n. So, this whole thing is a d by d matrix. So, J can be written as a quadratic form. So, let us give a name to this. What is this matrix? Xi minus x bar is the mean of xi. So, xi minus x bar transpose summed over I is equal to 1 to n is nothing but the covariance matrix, right. For a random vector x, the covariance matrix is defined as expected value of x minus mu x into x minus mu x transpose. Now, if I do not know how to evaluate such an expectation, I can evaluate it as a sample mean, and this is nothing but the sample mean estimate of that expectation. So, this is the data covariance matrix. As a matter of fact, we come across the data covariance matrix earlier when we did the Fisher linear discriminant. So, S is nothing but the data covariance matrix and J now can be written as Uj transpose S Uj, J is equal to m plus 1 to D. So, now my mean square error given any subspace defined by the U1 to UM plus 1 to UD, the mean square error in approximating a vector by its projection onto the semi-dimensional subspace is given by J is equal to m plus 1 to D Uj transpose S Uj, where S is the data covariance matrix. So, my job now is to find Uj's to minimize this. Okay. So, we need to find Uj's. Finding Uj's is same as finding the correct subspace to minimize J. Okay. So, what we need to minimize is essentially a quadratic form of a matrix with respect to vector. Of course, here I need to minimize some of such quadratic forms with respect to vectors which are constrained to be orthonormal, constrained to have norm 1 and orthogonal to each other. Okay. So, let us just look at how one minimizes a quadratic form. Suppose I want to find a vector u, to minimize u transpose S u subject to the constraint the norm of u is equal to 1, right. This is a constraint optimization problem that we already seen when we started with SVM. So, you want to maximize minimize this objective function subject to this constraint. So, we have to write a Lagrangian. So, the Lagrangian will be u transpose S u plus lambda times 1 minus u transpose u, right. So, this is the Lagrangian for this constraint optimization problem, and to find the optimum we need to equate the gradient of the Lagrangian to 0. Gradient what I am trying to find is u. So, I am optimizing it with respect to the vector u. So, gradient with respect to u, that gives me S u, 2 will go away anyway from both sides, and this side I will get minus lambda u. So, equating gradient to 0, we get S u is equal to lambda u. What is this equation? U is a vector, S is the given matrix. So, S u is equal to lambda u is nothing but the eigenvector equation for the matrix. So, this shows that any u that minimizes this has to be a eigenvector of the matrix S, right. This means u should be an eigenvector of S. So, if I want to minimize u transpose S u subject to u transpose u is equal to 1, then u has to be an eigenvector. Which eigenvector? We can actually plug this eigenvector property into our objective function. So, if I take u to be any eigenvector, what is the value of my objective function? U transpose S u is nothing but lambda u, u transpose lambda u, u transpose u is 1. So, that is lambda, right. So, if I want to minimize u transpose S u subject to the constraint that u transpose u is equal to 1, then u has to be an eigenvector, say corresponding to some eigenvalue lambda, and then if I take any eigenvector corresponding to eigenvalue lambda, the actual value of u transpose S u is nothing but lambda. How can this value be lambda? Is lambda a real number, a complex number? Hey, this can be lambda because lambda is a real number. Why is lambda a real number? As I said, this is the data covariance matrix. As you already know, the data covariance matrix is real, right? Of course, is it's easy enough to see. It's if all xi's are real, it's real, and is also symmetric. That is also quite easy to see. because of the outer product form, the matrix that you get is symmetric. So, S is a real symmetric matrix and hence all its eigenvalues are real. Right. So, if I want to minimize U transpose S2 subject to U transpose is equal to 1, then the minimizing U has to be a eigenvector, and if I take it to be eigenvector with eigenvalue lambda, then the value of U transpose S2 is equal to lambda, which means to actually minimize it, I need to take the eigenvector which corresponds to the least eigenvalue. Now, coming back to our problem, we want to minimize J is equal to m plus 1 to d Uj transpose S Uj, right, where our constraints are not only that Uj's are orthogonal, Uj's are unit norm, that is Uj transpose Uj is equal to 1, they are also orthogonal, right, Uj transpose Ui equal to 0 if I is not equal to j. With those constraints, I want to minimize this. Because we can once again write the Lagrangian and do dirty algebra, but we do not need to do all that, because I know for any one of these terms, if I want to minimize, the U has to be a eigenvector, right. So, ultimately all U's have to be eigenvectors. Now, I can there are S is a d by d matrix, there are d possible eigenvectors corresponding to d possible eigenvalues, and if I choose Uj to be any one eigenvector, I know Uj transpose S Uj will be the corresponding eigenvalue. So, this particular j would be sum of eigenvalues, which eigenvalues? The eigenvector that you picked up, the eigenvalues correspond to the eigenvectors you picked up. Now, I want this to be as small as possible. So, what does that mean? Now, we know because S is symmetric, all eigenvalues are real, and also it will always have a set of eigenvectors which can be orthonormal. So, S will have orthonormal set of eigenvectors, its eigenvalues are real, and the eigenvectors of S will span the space. So, eigenvectors of S can be an orthonormal basis for RD, right. I know so I can take the eigenvectors of S to be orthonormal basis for RD, then they satisfy the constraints of Uj. Now, we already know that any eigenvector will satisfy the gradient equal to 0 equation. So, essentially we have to ask which eigenvector to choose to minimize this, right. Any eigenvector I pick here, right, will be the Uj transpose S Uj is the eigenvalue, and obviously I can't repeat any eigenvector because I want Uj's to be orthogonal, they have to span the space. So, that tells me that the best I can do is to make my, so I have to pick I want to minimize this sum over j is equal to m plus 1 to d, that means I have to pick m plus 1 up to ud. So, I need to pick m plus 1 m plus 2 up to ud, and each one of them has to be a distinct eigenvector of S, and whichever eigenvector I pick up, that term in this sum transfer to the corresponding eigenvalue. So, which means m plus 1 2 up to ud should be the d minus 1 eigenvectors corresponding to the least d minus 1 eigenvalues. You take the eigenvalues of S, take the least d minus m eigenvalues and take the corresponding eigenvectors, that is the least I can make this J to be. So, what we have now shown is that if I want to minimize this, my choice of m plus 1, m plus 2 up to ud or the d minus m eigenvectors correspond to the least d minus m eigenvalues. Of course, minimizing this I will be fixing only m plus 1 up to ud. Why is that so? Because my J just turns out to be that, right. When we did that, my J turns out to be that because my xi minus x tilde up to first term, up to first m terms in the summation xi and x tilde are same, right, and hence my xi minus x tilde sums over only j is equal to m plus 1 to d of something into uj. So, ultimately my j turns out to be this, right. So, because my j turns out to be this, when I minimize that, I essentially pick um plus 1 to ud. But does it mean that I have choice about remaining? I do not, because the um plus 1 to ud completely specify the orthogonal complement to the m dimensional space that I want to be in. So, my optimal m dimensional space is one whose orthogonal complement is um plus 1 to ud, which means an orthonormal basis for that space is u1 to um. Right. So, ultimately what we have shown is that if I want x tilde, the m dimensional projection onto the m dimensional subspace, to be close to the original xi in the sense of minimizing mean square error, then the m dimensional subspace has a orthonormal basis given by u1 to um, where u1 to um are the eigenvectors of the data coherence matrix S corresponding to the top m eigenvalues. Okay. So, let us sum this up. So, given some data x1 to xn all living in the d-dimensional real Euclidean space, we do a lower dimensional representation as follows. We first form the data coherence matrix. S is 1 by n, I is equal to 1 to n, xi minus x bar transpose. This is a d by d matrix. Okay. Then we find all its eigenvectors. Let us say u1 to ud be the orthogonal set of eigenvectors, because S is real symmetric. It will have a complete set of eigenvectors, meaning its eigenvectors span the space. Since its eigenvectors span the space, I can actually make the eigenvectors be orthogonal, an orthogonal set of eigenvectors, and then of course, I can normalize them. So, I can have a orthonormal set of eigenvectors of S. Let us say u1 to ud are that such eigenvectors which are arranged in a decreasing order the corresponding eigenvalue. That means, u1 corresponds to the highest eigenvalue, u2 corresponds to the next highest eigenvalue, and so on. And I can talk about highest and next highest eigenvalue, because the eigenvalues are all real, because S is real symmetric. Okay. Once I have this complete eigenspectrum arranged like this, my low dimensional approximation now xi tilde is for j is equal to 1 to m xi transpose uj, where this u1 to um are the eigenvectors corresponding to top m eigenvalues of S, and then there is a constant j is equal to m plus 1 to d x bar transpose uj. Okay. This is my low dimensional approximation. I can slightly rewrite it. What I can do is, I can from each of these terms I can subtract x transpose uj and then add x transpose uj. That means, I will be adding j is equal to 1 to m x transpose uj to this term. So, I can write my x tilde as j is equal to 1 to m xi transpose uj minus x bar transpose uj. What I did is, from each of these terms I subtract x bar transpose uj. So, now I have got j is equal to 1 and plus this other term j is equal to 1 to d x bar transpose uj. Now, I can to get all my x bar transpose uj terms together, right. Once I subtract them, I have to add it. I already have m plus 1 to d and I am adding j is equal to 1 to m. So, I am adding j is equal to 1 to d, right. Now, j is equal to 1 to d x bar transpose uj is nothing but the representation of x bar in the coordinate system of uj. So, this entire sum is nothing but x bar. So, I can write it as x bar xi transpose uj minus x bar transpose uj plus x bar. This is my low dimensional representation. Writing like this is nice, because if I assume x bar to be 0, then it is simply xi tilde is xi transpose uj, first m components. Essentially, first m components in the coordinate system of the eigenvectors. So, instead of what my original coordinate system, I now represent my axis in the coordinate axis of the eigenvectors and then take the first m components. The extra terms here come only to take care of the bias, that means the non-zero mean of the data, and this never causes any problem, because you can always work with mean subtract data. If you give me x1, x2, xn as data, I can actually redefine x1 prime, x2 prime, xn prime, where xi prime is xi minus x bar. So, now these prime variables have 0 mean, I can always work with 0 mean data, and the covariance matrix the original data is same as the mean subtracted data. So, my UGS will be the same. So, without losses generally I can assume x bar to be 0. From now on we will write these expressions with x bar equal to 0. So, that they are much simpler. As I already told you, this does not look like an m dimensional vector. Of course, it lives in m dimensional subspace because this is just a constant. So, this is expanded in terms only u1 to um. So, to represent xi tilde you need to give me only m numbers, right, but it is still written in a vector notation as a d-dimensional vector because each of the UGS are d-dimensional. We can of course rewrite it as a d vector. So, as I said in our representation, xi tilde is a d-dimensional vector, right, because each of the UGS are d-dimensional vectors. But we can obviously write it as an m-dimensional vector because it is an m-dimensional subspace of Rd. How do you write it as m-dimensional vector? So, xi tilde can be written as u1 transpose xi, u2 transpose xi, so on, right. So, it becomes A transpose xi, written as a vector now of d components, m components, right. Essentially what it means is that once we take x bar to be 0, essentially I can write as m component vector, where the first component is xi transpose u1, second component is xi transpose u2 and so on. So, that is what this representation is. So, I can actually write xi tilde as A transpose xi, where A is a d by m matrix, this matrix, whose columns are the vectors u1 to um, right. So, you make a matrix whose columns are the eigenvectors, you take as many as you want and then write xi tilde as A transpose xi, where xi is the original data, then that is the lower dimensional representation of x. Okay. It is in this sense that it is a linear transform. So, essentially you are projecting xi onto the space spanned by the eigenvectors u1 to um. Okay. Now, this is as far as the viewpoint of finding the best mean square approximation is concerned. So, let us look at the other viewpoint of maximizing variance, right. We want to find an m dimensional subspace in which the projected data would have the maximum variance. As you already said, the solution will turn out the same, that is, once again we have to project data onto the space spanned by u1 to um. The orthonormal eigenvectors correspond to the top m eigenvalues of the data covariance matrix. We will see it quickly, we will not even give as much detail for this proof as the earlier one. To get our hooks on, let us consider a one dimensional case. Let us say u1 is the unit vector for the one dimensional subspace that we want to find u1. So, the projected data will be xi transpose u1 along u1. So, xi transpose u1, this is the vector notation. So, its mean will be x bar transpose u1. What will be its variance? xi transpose u1 minus x bar transpose u1 whole square, summed over I is equal to 1 to n, 1 by n. This will be 1 by n, sum I is equal to 1 to n, u1 transpose xi minus x bar transpose u1. We already know what this is, because 1 by n I is equal to 1 to n xi minus x bar into xi minus x bar transpose is s. This is u1 transpose s1. Okay. And we already know that this is maximized if u1 is the eigenvector corresponding to the highest eigenvalue. See, maximizing and minimizing is the same, right. Essentially, if I equate the gradient to 0, I get solution which might be either maxima or minima. That tells me that it has to be an eigenvector, and for any particular eigenvector I take u1 to be, this u1 transpose u1 will be corresponding eigenvalue. So, if I want to maximize it, u1 should be the eigenvector corresponding to the maximum eigenvalue. If I want to minimize it, it should be eigenvector corresponding to the least eigenvalue. So, here we want to maximize it. So, my first vector u1 should be the eigenvector of data covariance matrix corresponding to the maximum eigenvalue. Okay. So, now suppose m is equal to 2 and we want to add one more direction. What is that we need? We need a u2 which has a unit norm, which is such that u1 transpose u2 is equal to 0 and the projected variance should be maximum. Once again we will get the same thing, and u2 should become the eigenvector corresponding to the second largest eigenvalue and so on. Okay. So, that is how we can say if you want an m dimensional subspace that the project data would have the highest variance, then that subspace is the one spanned by the m eigenvectors of S corresponding to the top m eigenvalues. Okay. These directions ui are called the principal directions, and the projected values ui transpose x and so on, they are called the principal components. That is why this entire way of finding it is called principal component analysis, right. So, to sum up, the PCA is essentially a projection of the data vectors onto a space spanned by the eigenvectors of the covariance matrix, right. So, this is a linear transform of the original data x tilde J transpose x, where columns of A are the eigenvectors. Of course, I can choose all of them, right. Even then, I am transforming data into a better data, because essentially to take by using only top m eigenvectors, right. So, that I make A to be D by M matrix. So, that x tilde will be m dimensional subspace. So, if I use only top m eigenvectors, we get dimensional reduction, right. Now, what will be the residual error? The residual error, as you already seen, J is equal to m plus 1 to D uj transpose S uj, which is nothing but the sum of the remaining eigenvalues. So, the residual is the sum of the least D minus m eigenvalues. So, find all the eigenvalues, look from the bottom most. So, keep adding them, that how much error you can tolerate, that many eigenvalues you can reject, that tells me what m I should use, right. This is often one way of deciding what m. I look at these eigenvalues, and based on this set how many eigenvalues I can reject. If I have got a few high eigenvalues and rest of the eigenvalues are all small, then along those eigendirections I do not have much variation. So, that component of the data is not important, I will only look at the top m eigenvalues. That is how PCA works. Okay. We will quickly look at a couple of generic variations of PCA. First is what is called a whitening transform, because so far we looked at PCA mainly for dimensional reduction, that is its main use. Most of the time it is used as a dimensional reduction technique, but there are other uses, we will just illustrate one. We can use PCA to find a linear transform of the feature vector. So, the transformed features are uncorrelated. When we considered our linear least squares as well as our neural networks and so on, we mentioned that it is always nice to normalize individual feature component. That is, we want each feature component to have 0 mean and unit variance. So, that can be done by taking each feature component, find its mean from the data, its sample mean from the data, so that the mean and variance of each feature component can be standardized. So, we discussed how we can normalize, so that each feature component has 0 mean and unit variance, but that does not mean that the features themselves are uncorrelated, that is still leaving the features. Using PCA, we can actually transform the feature vector, so that the components can become uncorrelated, which could be quite useful in pattern recognition. Okay. So, as earlier, let S be the data covariance matrix and lambda 1 to lambda d be the eigenvalues of S arranged in the decreasing order. U1 to UD be the corresponding eigenvectors, which are orthonormal. Remember that because S is real symmetric and has a complete set of eigenvectors, we can have a orthonormal complement an orthonormal set of eigenvectors of S, and they are arranged in the order of lambda 1 to lambda d, the decreasing order of the eigenvalues. Of course, then we will not particularly use the fact that they are decreasing values in the whitening transform. Let L be a diagonal matrix with lambda I being the diagonal entries, and let U tilde be the matrix whose columns are uj. So, U tilde be U tilde is the matrix of eigenvectors, and because these eigenvectors are orthogonal, U tilde is a orthogonal or unitary matrix. Okay. So, U tilde is a D by D matrix because there are D eigenvectors each of D dimensions. Okay. So, the eigenvector equation for S is S U tilde is U tilde L. So, I have written all the eigenvector equations together, because L is diagonal with lambda, this is nothing but the eigenvalue equation for S. Now, let me define a transformation of the vectors. So, I transforms xi's into zi's. Zi is given by L to the power minus half, where L is the diagonal matrix with the eigenvalues on the diagonal, L to the power minus half u tilde transpose x I minus x tilde, where x bar x I minus x bar, where x bar is the mean of the data vectors. Okay. Now, it is very easy to see that Z I has 0 mean now. This transformation makes Z I 0 mean simply because x I minus x bar has 0 mean. Okay. So, Z I will, if I add all the Z I's, this is a constant, then that will be same as summation x I minus x I bar, that will be 0. Okay. Now, so 0 mean we achieved. We are asking what is the covariance matrix of Z I. We want Z I's covariance matrix to be identity matrix, so that not only each Z I has unit variance, Z I Z j are uncorrelated. Okay. Let us calculate the covariance matrix of Z I. What is the covariance matrix of Z I? Z I Z I transpose, because Z I is 0 mean. Okay. So, let us substitute for Z I. Z I is nothing but L to the power minus half u tilde transpose x I minus x bar. Z I transpose is x I minus x bar transpose u tilde L to the power minus half. Now, I have this S matrix sitting in the middle, 1 by n is equal to 1 to n x I minus x bar transpose, put that in. So, I get L to the power minus half u tilde transpose S u tilde L to the power minus half. Now, because u tilde is the matrix of eigenvectors, S u is u L, right, S u tilde is u L. So, this is L to the power minus half u tilde transpose u L L to the power minus half. U is a orthogonal matrix, whose columns are orthogonal. So, u tilde is identity. So, this goes away, and now I get L to the power minus half L to the power minus half. This is diagonal matrix. So, this is a identity. So, the covariance matrix of the data Z I now is the identity matrix. What does this mean? If we transform x I to Z I by using Z I is equal to L to the power minus half u tilde transpose x I minus x bar, where x bar is the mean of the original data, and u tilde is the matrix whose columns are the eigenvectors of the data covariance matrix, and L is a diagonal matrix whose diagonals are the eigenvalues of the data covariance matrix. Then this transformation transforms vectors into 0 mean, unit variance, uncorrelated components. This can often be useful in many practices. For example, in naive Bayes, we assume different features are independent. This transformation can at least give you uncorrelatedness. Okay. A PCA used like this to make my feature vector components uncorrelated is called a whitening transform. Okay. So, this is another use of PCA. Apart from dimensional reduction, I can use PCA as a whitening transform. There is one other interesting take on PCA, that is worth knowing. To implement the PCA, we need to find eigenvalues and eigenvectors of S, the data covariance matrix is the D by D matrix. There can be situations when the feature vector dimension is large, right, and so large that, as a matter of fact, the number of examples I have is less than 3. What are such situations? Image based practice. When we think of, let us say I am doing face recognition. So, I take each face image as a pattern. So, if I simply think of it as a vector, suppose I have a 32 by 32 image, a very small, highly scaled down image, it still has 1000 components. Right. If I take 64 by 64, it has a million components. Right. But even at 32 by 32, 1000 component face image, if you want face recognition, how many different images can I get for one particular person? Maybe 20, maybe 10. I can't get 10,000 images. So, very often n will be much less than d, because I often work with more than 32 by 32 images, and I do not have so many face images of a single person, and even if I have all the face images put together, won't become too large. So, I may have d much larger than n, and I need to find the eigenspace of S. Okay. Now, when d is large, the finding the eigenvectors of S can be computationally expensive and also may be useless. Okay. Basically, because computationally expensive, we do not want to find all the eigenvalues. So, we are asking, because n is much less than d, is there a way I can find the eigenvectors of some other n by n matrix instead of this d by d matrix? We will show that it can be done. The main reason why we choose an n by n matrix is, S is given by this. So, each of xi, this is some vector. So, xi minus x bar transpose, this is an outer product. So, if I take a vector A and I form the matrix A transpose, obviously it is a rank 1 matrix, because every column is a multiple of another column. So, because this is a rank 1 matrix, I am adding n rank 1 matrices. The rank of S can be at most n, which means I anyway know d minus n eigenvalues will be 0, because the rank will be n, and hence I do not need the eigenvector corresponding to that. I will not use them, because there are 0 eigenvalues. I would anyway drop those dimensions. So, I should be able to work with just n eigenvectors. If I want to work with n eigenvectors, I should be able to find eigenvectors of an n by n matrix. So, what n by n matrix should I do? So, let A be the n by d matrix whose ith row is xi minus x bar transpose. Then by definition S is 1 by n A transpose A, right, xi minus x bar transpose summed over I. Let ui be an eigenvector of S with an eigenvalue lambda for a eigenvalue that is greater than 0. So, that means 1 by n A transpose A into ui is lambda I ui. If I multiply both sides with A, that is a lambda I times A ui will be A times 1 by n A transpose A ui, because matrix multiplication associative, I can write as 1 by n, this is scalar, bring it out. I have A transpose and AU can be put in. That means, I have 1 by n A transpose times AU is lambda times AU. So, AUI is a eigenvector corresponding to the eigenvalue lambda I of the matrix 1 by n A transpose. A is an n by d matrix. So, A transpose is a n by n matrix. S is of course an A transpose A, but instead that if I do 1 by n A transpose, the AUIs are eigenvalues. So, if ui is an eigenvector of S 1 by n A transpose A for an eigenvalue lambda I, then lambda is also happens to be an eigenvalue of the n by n matrix 1 by n A transpose, and AUI is the corresponding eigenvector, which means for taking PCA now, I do not need to find the eigenvectors of S. I can work with the eigenvectors of the n by n matrix. Specifically, what can I do? Let Vi be the eigenvector corresponding eigenvalue lambda I of the n by n matrix 1 by n A transpose. I hope you remember what A is. A is the n by d matrix whose ith row is xi minus x bar transpose. So, S is actually 1 by n A transpose A. Instead of that, we are looking at 1 by n A transpose. 1 by n A transpose A is a d by d matrix. 1 by n A transpose is a n by n matrix. If Vi is the eigenvector, I know 1 by n A transpose Vi is lambda I Vi, and hence 1 by n A transpose A into A transpose Vi. So, if I multiply both sides of the equations A transpose, I can put A transpose A here and A transpose Vi here, because the associativity. So, 1 by n A transpose A into A transpose Vi is lambda I times A transpose Vi. So, I find all the eigenvectors Vi of 1 by n A transpose, which is an n by n matrix, and then I can get the eigenvectors of 1 by n A transpose A, which is my Dada-Cohen's matrix, as simply A transpose Vi. Thus, we get all the required eigenvectors of S. Right? So, this is how one handles high dimensional PCA. So, we will stop the PCA here. So, we will not come to feature vector selection anymore. Next class we will look at a few other special topics of pattern recognition. Thank you.